Welcome back to the Sleep Lab. Racing through space at 58 kilometers per second, something impossible has invaded our solar system. 3I/ATLAS, an ancient wanderer older than Earth itself, breaking every rule we know about interstellar objects. It's too fast, too active, and carrying chemicals that shouldn't exist after billions of years in the cosmic void. Some scientists whisper it might not be natural at all. What if everything we believed about visitors from deep space was wrong? What if this mysterious traveler is about to rewrite astronomy itself? If you're ready to uncover the cosmos's most controversial discovery, make sure you're subscribed and hit that notification bell. Because tonight, we're diving deep into why 3I/ATLAS is the most rule-breaking object ever to enter our cosmic neighborhood. Chapter 1. The arrival that shouldn't be possible. It's difficult for us humans to fully comprehend the enormity of space. We are comfortable in our own cosmic neighborhood, the solar system, and are used to familiar faces like Jupiter, Mars, and of course, Earth. But out there, over 18 billion kilometers away from the Sun and beyond the heliopause, lies the cold oblivion of interstellar space. In the vast silent expanse of the Milky Way, our solar system is not an island. It is a traveler on a galactic current, periodically crossing paths with messengers from other stellar shores. For millennia, these encounters went unnoticed, lost in the infinite darkness between stars. The two Voyager probes are the only human-made objects ever to cross the threshold into this cosmic wilderness, carrying our first tentative messages to whatever might be listening in the void. Until recently, only two known objects had ever made the opposite journey, passing from interstellar space into our solar system. These were the famous 1I/Oumuamua in 2017 and 2I/Borisov in 2019, which brought with them the thrill, and perhaps even fear, of being visited by something from the depths of space that humans cannot hope to reach in our lifetimes. Each was a profound discovery, a single data point hinting at the nature of planetary systems beyond our own, visitors from stellar neighborhoods we can barely imagine. Oumuamua arrived like a ghost, tumbling through our solar system with its strange elongated shape and mysterious acceleration, departing almost as quickly as it came. It left behind more questions than answers, a cosmic riddle wrapped in an enigma. Borisov followed 2 years later, more familiar in its cometary behavior, yet still alien in its composition, carrying chemical signatures of a stellar system fundamentally different from our own. In the 6 years since these visits, we had been enjoying some respite from the cosmic unknown. Astronomers continued their patient vigil, scanning the skies with ever more sophisticated instruments, knowing that eventually another messenger would arrive from the galactic depths. But when it came, it would eclipse its predecessors in nearly every respect, heralding a new era in the study of extrasolar planetesimals. On July 1st, 2025, that moment arrived. A recent observation forced the astronomical community to sit up and pay attention once more as telescopes detected something extraordinary racing toward our Sun from the direction of the constellation Sagittarius. This third confirmed interstellar object would prove to be not merely another cosmic rock, but a pristine, tangible sample from a planetary system that likely formed billions of years before our own, a relic from the galactic dawn. Racing through the silent darkness between stars at an incomprehensible 58 kilometers per second, 3I/ATLAS represents everything we thought was impossible about interstellar visitors. Its speed alone defies comprehension. Imagine running the length of 580 football pitches every single second. That's its hyperbolic excess velocity relative to the Sun, a velocity so extreme it dwarfs its predecessors. Oumuamua's 26 kilometers per second and Borisov's 32 kilometers per second seem pedestrian by comparison. Such velocity cannot be achieved by any object originating in our solar system, even with gravitational assists from all the giant planets. It is the indelible signature of a body that has journeyed across the galaxy, propelled by the ancient dynamics of its birth system and shaped by billions of years of interstellar wandering. But speed is just the beginning of what makes 3I/ATLAS so extraordinary. Designated with the official name that reflects both its interstellar origin and its cometary classification, 3I/ATLAS, for its status as the third confirmed interstellar visitor, and C, 2025 N1 Atlas for its cometary nature. This ancient wanderer carries within its pristine nucleus chemical fingerprints of a time when our galaxy was fundamentally different from the stellar neighborhood we know today. When the first generations of planets were forming around metal-poor stars in the thick disk of the Milky Way, long before our Sun even existed, the building blocks of 3I/ATLAS were already assembling in a distant protoplanetary disk. For 7 to 11 billion years, roughly twice the age of our entire solar system, this cosmic time capsule has been wandering through the harsh environment of interstellar space, subjected to cosmic ray bombardment, temperature extremes, and the gravitational perturbations of countless stellar encounters. Yet somehow, it has preserved within its nucleus the chemical signatures of its birth environment, maintaining its structural integrity across cosmic epochs that dwarf human comprehension. The discovery timeline itself reads like a technological thriller. The Atlas Survey, NASA's asteroid hunting network designed to protect Earth from potentially hazardous objects, captured the first images of this interstellar intruder on that fateful July evening in Chile. But as astronomers dove deeper into archived data, they made a remarkable discovery. This cosmic visitor was no stranger to their instruments. Multiple observatories had been unknowingly tracking it for weeks, with the most significant recovery coming from NASA's TESS satellite, which had serendipitously observed the object nearly continuously between May 7th and June 3rd, 2025. Perhaps most prophetically, the newly commissioned Vera C. Rubin Observatory in Chile had also captured images of 3I/ATLAS during its science validation phase, a full 10 days before the official discovery. This wasn't merely a footnote in astronomical history, but a powerful preview of the future. Had the Rubin Observatory's validation program begun just 2 weeks earlier, it would have claimed the discovery for itself, heralding a new age in cosmic archaeology, where dozens of interstellar visitors might be detected each year, rather than one every few years. What emerged from this coordinated global effort was an object that challenged every assumption about what interstellar visitors should look like. Unlike the faint fleeting glimpse we had of Oumuamua, 3I/ATLAS blazed across our detectors with remarkable brightness. Between late May and its July discovery, something extraordinary occurred, a dramatic brightening that saw its magnitude surge as solar radiation began penetrating its ancient surface, sublimating ices that had remained frozen for billions of years. The resulting cloud of gas and dust created a glowing halo that scattered sunlight, transforming a dark, distant speck into one of the brightest interstellar objects ever detected. Early estimates based on this brightness suggested a nucleus diameter that defied belief, potentially 15 to 20 kilometers across, making it not just the largest interstellar object ever detected, but potentially larger than many famous comets in our own solar system. While subsequent analysis would revise these estimates downward, 3I/ATLAS still comfortably holds the record as the most massive interstellar visitor we've ever encountered. But perhaps the most shocking revelation came from what the object was doing. Within days of its discovery, multiple observatories reported tentative signs of cometary activity, a diffuse halo of dust and gas, and tail-like features extending from the object. This wasn't just another interstellar asteroid like Oumuamua. This was a comet, actively sublimating its ancient ices as it approached our sun, releasing material that had been locked away since the formation of a distant planetary system billions of years ago. The implications were staggering. NASA's Neil Gehrels Swift Observatory made the first direct detection of water activity from the comet by observing ultraviolet emission from hydroxyl radicals, molecules that form when water vapor is broken apart by solar radiation. Here was smoking gun evidence that 3I/ATLAS is indeed a water ice-driven comet, operating according to the same fundamental processes that govern comets from our own solar system, yet carrying chemical signatures from an epoch when our galaxy was young and metal-poor. The rapid confirmation process marked a profound shift in the study of interstellar objects. The discovery of Oumuamua had been largely reactive. The object was already past its closest approach to the Sun and heading back to interstellar space when scientists fully realized what they were observing. In contrast, 3I/ATLAS was identified far out on its inbound trajectory, providing months of lead time for a coordinated global characterization campaign. This new paradigm represents the evolution from chance encounters to systematic discovery, from individual observations to global coordination, from reactive science to proactive cosmic archaeology. As we stand on the threshold of this new era, 3I/ATLAS serves as both a spectacular final catch for the current generation of surveys and the inaugural test case for the next. Its story demonstrates how a single object, racing through space faster than anything in our solar system, older than the Earth itself, and carrying pristine samples from the galaxy's youth, can arrive unannounced and force us to reconsider everything we thought we knew about planetary formation, interstellar travel, and our place in the cosmic community. The ancient wanderer had arrived, and nothing would ever be quite the same. Chapter 2. What's at stake? Rethinking how worlds form. Picture this. Every theory we have about how planets form, how life emerges, and when the universe became capable of harboring complex chemistry, is based on a single assumption: that heavy elements, the metals forged in stellar furnaces over billions of years, are absolutely essential for building worlds. We've spent decades studying our solar system, analyzing thousands of exoplanets, and constructing elaborate computer models that all point to the same conclusion. Rocky planets and water-rich comets could only form after generations of massive stars lived, died, and scattered their atomic ashes across the galaxy. This process, we believed, took at least 8 to 10 billion years to create the chemical conditions necessary for Earth-like worlds. But what if this fundamental assumption, the bedrock of modern planetary science, is completely wrong? 3I/ATLAS isn't just another space rock tumbling through our cosmic neighborhood. It's a 4.6-kilometer wide time capsule that formed when our galaxy was barely half its current age, when the Milky Way was a chaotic, metal-poor environment supposedly incapable of creating substantial planetary building blocks. This ancient wanderer should not exist, yet here it is, blazing through our telescopes with an intensity that has left astronomers speechless. The water vapor streaming from its nucleus has been frozen solid for over 4 billion years, longer than Earth has existed. The organic compounds embedded in its rocky core formed under chemical conditions so different from our own solar system that they might as well have come from an alien universe. The stakes couldn't be higher. If 3I/ATLAS represents what we think it does, a pristine sample from the galaxy's youth, then we need to completely rewrite the timeline of cosmic evolution. Everything we thought we knew about when planets could form, when life's building blocks became available, and how long the universe has been capable of harboring complex chemistry suddenly becomes obsolete. Think about the implications for a moment. Current models suggest that Earth-like planets could only begin forming about 6 to 8 billion years ago, when stellar nucleosynthesis had finally enriched the galaxy with enough heavy elements to build rocky worlds and complex molecules. This timeline puts Earth among the first generation of potentially habitable planets in the Milky Way, making us cosmic pioneers in the grand story of life. But 3I/ATLAS formed at least 7 billion years ago, possibly as much as 11 billion years ago, in an environment we considered hostile to planetary formation. If large, water-rich objects like this ancient comet were common in the early galaxy, then potentially habitable worlds may have existed when the universe was less than a third of its current age. The scientific revolution hidden within this single object extends far beyond academic astronomy. The search for extraterrestrial life has always been constrained by what researchers call the metallicity bottleneck, the assumption that complex chemistry requires heavy elements forged in multiple generations of stellar evolution. SETI programs focus on relatively young, metal-rich star systems like our own, believing that older metal-poor stars lack the chemical diversity necessary for life. But 3I/ATLAS suggests that this bottleneck might be an illusion, a product of our limited perspective, rather than a fundamental cosmic constraint. If water-rich planetesimals were forming efficiently around ancient, metal-poor stars, then the chemical prerequisites for life, water, organic compounds, and complex carbon chemistry, have been available throughout most of cosmic history. This pushes the potential emergence of life back by billions of years and dramatically expands the number of stellar systems that could harbor biological activity. We're not just talking about a few more potentially habitable worlds. We're talking about fundamentally reconceptualizing the prevalence of life in the universe. The chemistry revealed by 3I/ATLAS is equally revolutionary. Spectroscopic analysis has detected water vapor, carbon dioxide, carbon monoxide, and complex organic compounds, the full suite of materials needed for prebiotic chemistry. But these aren't just any organic compounds. They're the same types of carbon-based molecules found in the most primitive meteorites in our solar system, suggesting that the fundamental processes of organic synthesis operate consistently across vastly different stellar environments and cosmic epochs. Perhaps most intriguingly, the isotopic ratios measured in 3I/ATLAS's outgassing materials don't match what we'd expect from a metal-poor environment. The nitrogen-to-carbon ratio, the deuterium content, and the distribution of heavy elements all suggest more efficient chemical processing than theoretical models predict for the early galaxy. It's as if this ancient object formed in a stellar system that somehow accelerated the normal timeline of chemical evolution, creating complex chemistry billions of years ahead of schedule. But there's an even more profound implication lurking in the data. 3I/ATLAS didn't just form in the ancient galaxy. It survived the journey across billions of years and countless light-years of interstellar space, while preserving its volatile inventory. The object's high activity levels, producing about 40 kilograms of water vapor per second at a distance of 3.5 astronomical units from the Sun, indicate that a substantial fraction of its original ice content remains intact after eons of cosmic ray bombardment, temperature extremes, and gravitational perturbations. This survival story suggests that interstellar space isn't the hostile, sterilizing environment we once believed. Large icy bodies can preserve complex chemistry across cosmic timescales, serving as vehicles for transporting the building blocks of life between stellar systems. If objects like 3I/ATLAS are common, and initial population estimates suggest they might be, then the galaxy has been seeded with organic chemistry for most of its existence through a vast network of wandering planetesimals. The technological implications are equally staggering. Understanding how planets formed in metal-poor environments could revolutionize our approach to terraforming and space colonization. If substantial worlds can assemble without the heavy element abundance we see in our solar system, then potentially habitable planets might exist around a far broader range of stellar types, including the long-lived red dwarf stars that will dominate the galaxy's future for trillions of years. Moreover, the detection and characterization of 3I/ATLAS demonstrates that we've entered a new era of cosmic archaeology. Advanced sky surveys and rapid response spectroscopy can now identify and analyze visitors from distant stellar systems in real time, turning each interstellar object into a direct probe of planetary formation processes we could never otherwise observe. We're no longer limited to studying our own solar system's history. We can directly sample the chemical signatures of planetary formation across the galaxy and throughout cosmic time. But perhaps the most unsettling implication is what 3I/ATLAS suggests about our cosmic loneliness. If complex chemistry has been available for most of the galaxy's history, if potentially habitable worlds have existed for billions of years longer than we thought, then where is everybody? The famous Fermi paradox becomes even more paradoxical when we push the timeline for potential life back by half the age of the universe. Either life is far rarer than the chemical evidence suggests, or we're missing something fundamental about how biological complexity emerges and evolves. The ancient wanderer, now racing through our solar system, carries with it the potential to revolutionize our understanding of planetary formation, the prevalence of life, and our place in cosmic history. Every spectrum captured from its glowing coma, every measurement of its unusual trajectory, and every chemical signature detected in its ancient nucleus adds another piece to a puzzle that could reshape astronomy, astrobiology, and our fundamental conception of when and where life can emerge in the universe. This isn't just about one remarkable comet. This is about discovering that the universe has been far more alive, far more chemically active, and far more capable of creating the conditions for life than we ever dared imagine. The rules of cosmic evolution are being rewritten by a visitor from the galaxy's dawn, and the implications will ripple through science for generations to come. Chapter 3. The Race to Discovery, a Global Astronomical Effort. The story of 3I/ATLAS begins not with a single moment of discovery, but with a network of robotic sentinels scattered across our planet, each one methodically scanning the heavens night after night, waiting for something extraordinary to appear. What unfolded in the summer of 2025 would demonstrate the breathtaking power of modern astronomy. A coordinated global effort that transformed a faint speck of light into the most controversial interstellar visitor ever detected. Picture this. While most of the world slept on July 1st, 2025, a robotic telescope in the Chilean desert was about to make history. The Atlas telescope at El Sos Observatory, designated W68, was performing its routine systematic sweep of the southern sky, pointing toward the constellation Sagittarius, that dense stellar region harboring our galaxy's central supermassive black hole. Hidden among countless stars was an object making a beeline toward our solar system, traveling at a velocity that would soon defy all comprehension. But here's what makes this discovery truly remarkable. ATLAS wasn't just any survey telescope. This NASA-funded network represents humanity's planetary defense system, 4 strategically positioned telescopes across Chile, South Africa, and Hawaii, each capable of capturing around 800 images per night. Their combined efforts had already registered over 1,200 near-Earth objects. But Atlas possessed something that set it apart from other sky surveys. While most telescopes would be blinded by the bright disc-shaped region of our galaxy, ATLAS could peer directly into this cosmic maelstrom, a capability that would prove absolutely crucial that fateful July night. Initially designated with the prosaic name A11PL3Z, this faint speck of light immediately triggered alerts at the Minor Planet Center in Cambridge, Massachusetts. Think of the MPC as mission control for cosmic discoveries, the designated global authority for tracking and cataloging every minor body in our solar system. When their computers processed the data from Chile, astronomers realized they were witnessing something that shouldn't exist. The object's motion was so unusual, so unlike anything native to our solar system, that suspicions were instantly raised about its origin. Within hours, the astronomical community erupted into coordinated action. The MPC issued an electronic circular detailing the object's trajectory, and what they found was staggering. This wasn't just another asteroid or comet. Its orbital parameters suggested it had come from the depths of interstellar space, moving with a speed and direction that spoke of origins beyond our sun's gravitational influence. But the real detective work was just beginning. As astronomers dove deeper into archived data, they made a discovery that would send shockwaves through the scientific community. This cosmic visitor was no stranger to their instruments. Like archaeological layers waiting to be uncovered, scientists began mining through weeks of stored images from telescopes around the world. The Zwicky Transient Facility in California had captured it. 3 other Atlas telescopes had recorded its passage. Each observation helped refine their understanding of this mysterious wanderer's path through our solar system. Then came the most significant breakthrough of all. NASA's Transiting Exoplanet Survey Satellite, TESS, designed to hunt for planets around distant stars, had serendipitously observed the object nearly continuously between May 7th and June 3rd, 2025. These space-based observations provided the earliest known photometric data, extending the observational baseline and allowing astronomers to trace the object's journey back through months of interstellar approach. Imagine the excitement. They could literally rewind time and watch this ancient visitor's approach to our cosmic neighborhood. Perhaps most prophetically, the newly commissioned Vera C. Rubin Observatory in Chile had also captured images of 3 I/ATLAS during its science validation phase, starting on June 21st, a full 10 days before the official Atlas discovery. This wasn't merely a footnote in astronomical history. Had the Rubin Observatory's validation program begun just 2 weeks earlier, it would have claimed the discovery for itself, heralding the new age of cosmic archaeology that awaits us in the coming decade. With all this data combined, the mathematical proof became undeniable. The MPC's analysis revealed an orbit with exceptionally high eccentricity, approximately 6.14. This single number was the smoking gun that definitively proved the object had originated from interstellar space, far beyond the gravitational influence of our Sun. On July 2, 2025, the MPC issued Minor Planet Electronic Circular MPAC 2025 N12, formally announcing that the object was of interstellar origin and bestowing upon it the official designation 3I/ATLAS. But the surprises weren't over. Within days of the announcement, multiple observatories began reporting something that would transform this discovery from remarkable to absolutely revolutionary. The Deep Rapid Survey in Chile, the Lowell Discovery Telescope in Arizona, and the Canada-France-Hawaii Telescope at Mauna Kea all detected tentative signs of cometary activity, a diffuse halo of dust and gas surrounding the object, with a short tail-like feature extending from its nucleus. The implications hit the astronomical community like a thunderbolt. This wasn't just another interstellar asteroid like Oumuamua. This was a comet, actively sublimating ancient ices as it approached our Sun, releasing material that had been locked away since the formation of a distant planetary system billions of years ago. For the first time in human history, we were witnessing the awakening of an interstellar comet, watching as solar radiation penetrated its surface and began vaporizing ices that had remained frozen since before Earth existed. The rapid confirmation process that followed marked a profound shift in the study of interstellar objects. When Oumuamua was discovered in 2017, it had been largely reactive science. The object was already past its closest approach to the Sun and heading back to interstellar space when scientists fully realized what they were observing. In stark contrast, 3I/ATLAS was identified far out on its inbound trajectory, providing months of lead time for what would become the most coordinated global characterization campaign in astronomical history. Telescopes across 6 continents swung into action. The Hubble Space Telescope cleared its observation schedule. The James Webb Space Telescope allocated precious time for infrared spectroscopy. Ground-based observatories from Hawaii to Chile began round-the-clock monitoring. Amateur astronomers worldwide organized through social media platforms, creating a distributed network of observers that would provide nearly continuous coverage of this ancient wanderer's journey through our solar system. What emerged was a new paradigm in cosmic discovery, a seamless integration of space-based and ground-based assets, professional and amateur observations, automated detection systems, and human expertise. The discovery of 3I/ATLAS demonstrated how modern astronomy has evolved from the lonely observer with a single telescope into a globally coordinated enterprise capable of responding to cosmic events with unprecedented speed and precision. But perhaps the most remarkable aspect of this discovery was what it represented for the future. While current surveys have managed to find only 3 interstellar objects in 8 years, the Vera C. Rubin Observatory, whose pre-discovery imaging provided that tantalizing preview, is projected to discover dozens, perhaps hundreds of such objects over its initial decade of operations. The detection of 3I/ATLAS on the very cusp of this new era serves as both the spectacular final catch for the current generation of surveys and the inaugural test case for the cosmic archaeology revolution that lies ahead. As news of the discovery spread through scientific journals and social media alike, one thing became crystal clear. 3I/ATLAS represented far more than just another cosmic curiosity. It was a messenger from the deep past, carrying within its ancient nucleus the chemical fingerprints of planetary formation from an epoch when our galaxy was fundamentally different. And thanks to the remarkable global effort that brought it to light, humanity was about to get its first detailed look at materials older than our entire solar system, a window into the cosmic conditions that prevailed when the universe was young and the first worlds were taking shape around distant stars. The race to discovery was complete, but the real adventure was just beginning. Chapter 4. A Rule Breaker's Passport. Orbit, Speed, and the Surprise of 3I/ATLAS. The orbit of 3I/ATLAS serves as its cosmic passport, encoding a story so extraordinary that it has left astronomers questioning everything they thought they knew about visitors from beyond our solar system. Every parameter of its trajectory screams impossibility. Every calculation reveals anomalies that shouldn't exist, and every measurement deepens a mystery that has transformed from scientific curiosity into the most controversial interstellar object debate in modern astronomy. To understand why this ancient wanderer is breaking all the rules, we need to dive into the mathematics of celestial motion. Because in space, numbers don't lie, and the numbers surrounding 3I/ATLAS are absolutely staggering. The fundamental proof of any object's interstellar nature lies in a single crucial measurement: its orbital eccentricity. This seemingly simple number tells us everything about an object's relationship with our Sun and its ultimate cosmic fate. Think of eccentricity as the universe's identification system. Objects in perfectly circular orbits, like some of our planets, have an eccentricity of 0. Most comets and asteroids native to our solar system have eccentricities between 0 and 1, creating those familiar elongated elliptical paths we see in textbooks. An eccentricity of exactly 1 represents the cosmic speed limit for bound objects, the precise velocity needed to escape our Sun's gravitational embrace forever. But 3I/ATLAS. It obliterates these familiar categories with an eccentricity of approximately 6.14. Let that sink in for a moment. This isn't just slightly above the escape threshold. It's 6 times beyond what should be possible for any natural object we've ever encountered. To put this in perspective, the infamous Oumuamua, which caused such a sensation in 2017, had a modest eccentricity of 1.2. Borisov, the second confirmed interstellar visitor, managed 3.6. But 3I/ATLAS has arrived with an eccentricity that defies not just our experience, but our theoretical models of what's possible in galactic dynamics. This extreme eccentricity translates into velocity numbers that seem ripped from science fiction. Picture this. 3I/ATLAS is moving so fast that it could traverse the length of 580 football fields every single second. That's its hyperbolic excess velocity of 58 kilometers per second relative to our Sun, a speed so extreme that it makes its interstellar predecessors look like they're crawling through cosmic molasses. When 3I/ATLAS was first detected near Jupiter's orbit, it was already screaming through space at 61 kilometers per second. But here's where it gets truly mind-bending. As it approaches perihelion, its closest point to the Sun, gravitational acceleration will boost its velocity to a staggering 68.3 kilometers per second. To achieve such speeds naturally, an object would need to be hurled from its birth system with forces that challenge our understanding of planetary ejection mechanisms. But speed alone isn't what's keeping astronomers awake at night. The most scientifically puzzling and controversial aspect of 3I/ATLAS lies in its geometric relationship to our solar system, specifically its orbital inclination of 175.11 degrees. This number has ignited a firestorm of debate that extends far beyond academic journals. Here's why. An inclination of 180 degrees would represent a perfectly retrograde orbit, moving in exactly the opposite direction to our planets, but precisely aligned with their orbital plane. 3I/ATLAS is traveling backward relative to planetary motion, but its path is tilted by only about 5 degrees from the ecliptic, the fundamental plane in which all our solar system's planets orbit. The statistical probability of this alignment occurring by pure chance? A mere 0.2%. Think about what this means. In a galaxy containing hundreds of billions of stars, each potentially ejecting planetesimals in random directions, 3I/ATLAS somehow arrived at our solar system on a trajectory that appears almost surgically precise. It's as if this ancient wanderer chose the most convenient highway through our planetary neighborhood, following a path that maximizes its encounters with the inner solar system's most significant worlds. This geometric precision has split the astronomical community into two fundamentally different camps, each interpreting the same data through radically different lenses. From the mainstream scientific perspective, this alignment represents a fascinating statistical fluke. Improbable, yes, but inevitable, given the vast number of ejected objects wandering our galaxy. Perhaps 3I/ATLAS originated from a stellar system with specific dynamical properties that preferentially eject objects along the galactic plane. Or maybe our detection surveys, optimized to find objects near the ecliptic, are creating observational biases that make such alignments appear more common than they actually are. But there's another interpretation, one that has captured public imagination and triggered intense scientific debate. Harvard astronomer Avi Loeb and his collaborators have proposed that the 0.2% probability isn't evidence of cosmic coincidence, but of cosmic intelligence. In their framework, the orbit appears fine-tuned to enable efficient reconnaissance of our solar system's inner planets. Precisely the trajectory an extraterrestrial probe might select for systematic observation of our cosmic neighborhood. The object's path takes it on what can only be described as a grand tour of the inner solar system. Arriving from the direction of Sagittarius, it follows an asymptotic approach that brings it uncomfortably close to multiple planetary targets. The minimum orbit intersection distances reveal a series of encounters that seem almost too convenient. Mars at just 0.0179 astronomical units, Jupiter at 0.2467 astronomical units, and Venus at 0.65 astronomical units. These aren't independent coincidences. They're geometric consequences of 3I/ATLAS's controversial near-ecliptic alignment. But here's where the mystery deepens even further. The timing of 3I/ATLAS's perihelion passage, scheduled for October 30th, 2025, places its closest approach to the Sun during a period of solar conjunction, meaning it will be hidden from Earth's view by the Sun's overwhelming glare. This orbital geometry, with roughly a 7% probability for any random trajectory, provides what critics call the perfect opportunity for concealment. Proponents of artificial origin theories suggest this timing could enable a clandestine reverse solar Oberth maneuver. A hypothetical spacecraft performing a braking burn at maximum velocity to enter a bound solar orbit, all while remaining invisible to Earth-based observers. It's a scenario that sounds like science fiction, but the physics are sound, and the observational consequences would be dramatic and easily detectable. The velocity requirements for such a maneuver are staggering. To transition from 3I/ATLAS's current hyperbolic trajectory into a bound solar orbit would require a velocity change of tens of kilometers per second, an engineering feat that would dwarf anything in human space exploration. But for a civilization capable of interstellar travel, such capabilities might be routine. Yet mainstream astronomy remains skeptical, and for good reason. The same geometric alignment that makes 3I/ATLAS's trajectory seem suspiciously artificial also makes it inevitable that any object passing through the ecliptic plane would encounter multiple planets. The apparent fine-tuning dissolves under mathematical analysis. These close approaches aren't separate anomalies requiring explanation, but different manifestations of the same geometric relationship. Moreover, the proposed stealth maneuver faces a crucial observational test. While Earth-based telescopes will indeed lose sight of 3I/ATLAS during solar conjunction, multiple spacecraft throughout the inner solar system will maintain clear lines of sight. ESA's JUICE mission, NASA's Juno orbiter, and various Mars-based assets will be perfectly positioned to track the object's motion during its closest solar approach. Any significant trajectory modification would be immediately apparent to these robotic observers. The December 2025 observations, when 3I/ATLAS re-emerges from behind the Sun, will provide the ultimate test. If the object continues on its predicted hyperbolic path, with no deviation beyond natural cometary outgassing effects, it will serve as powerful evidence against artificial intervention theories. But if significant trajectory changes are detected, well, that would mark one of the most profound discoveries in human history. What makes this controversy particularly fascinating is how it demonstrates the evolution of astronomical methodology. Previous interstellar visitors arrived with less dramatic characteristics and shorter observation windows. Oumuamua was discovered after perihelion, already heading back to interstellar space. Borisov, while more thoroughly studied, never generated the same level of statistical anomalies. 3I/ATLAS, detected far from the Sun, with months of observation time ahead, has provided astronomers with an unprecedented opportunity to test extraordinary hypotheses using rigorous scientific methods. Whether viewed as a natural wonder, preserving chemical signatures from the galaxy's youth, or as a potential artificial construct conducting reconnaissance, its trajectory serves as a cosmic Rosetta Stone encoding messages we're only beginning to decipher. The numbers don't lie. 3I/ATLAS is moving too fast, aligned too precisely, and timed too conveniently to be dismissed as just another cosmic rock. Whether these anomalies represent the natural consequences of galactic dynamics or something far more extraordinary, one thing is certain: this ancient wanderer has shattered every rule we thought governed visitors from the stars, and the answers we discover may reshape our understanding of our place in the universe forever. Chapter 5. Not Your Average Comet: Chemistry, Activity, and Physical Enigmas. The first rule 3I/ATLAS broke was supposed to be simple. Interstellar objects should be dead, dark, and silent. After billions of years drifting through the cosmic void, exposed to radiation that would sterilize entire planets, any ice should have long since sublimated away into nothingness. Any organic compounds should have been torn apart by cosmic rays. What we should have found was a cold, inactive rock, a cosmic fossil bearing only the faintest traces of its ancient origins. Instead, 3I/ATLAS announced its presence with a spectacular light show that left astronomers scrambling to rewrite their textbooks. As this ancient wanderer approached our sun, something extraordinary began to happen. At a distance where most solar system comets remain dormant and inactive, 3I/ATLAS suddenly erupted into life. Between May and July 2025, observers watched in amazement as the object's brightness surged from a barely detectable magnitude 20 to a blazing 17.7, an increase that meant it was reflecting nearly 16 times more sunlight than just weeks before. This wasn't the gradual awakening astronomers expected from a comet slowly heating up. This was an explosion of activity that defied every model of how ancient interstellar ice should behave. The brightness surge revealed something that challenged fundamental assumptions about interstellar survival. Within days of the discovery announcement, multiple observatories reported the telltale signs of cometary activity: a diffuse glowing coma surrounding the central nucleus, and a distinctive tail stretching thousands of kilometers behind the object. But this wasn't just any ordinary comet awakening. Analysis revealed that 3I/ATLAS was outgassing water vapor at a rate of approximately 135 billion molecules per second, roughly 40 kilograms every second, while still over 3.5 astronomical units from the Sun. To put this in perspective, most comets from our own solar system barely show any activity at such distances. The fact that 3I/ATLAS was producing this much water vapor while still so far from our star suggested that either an unusually large fraction of its surface was active, over 20%, compared to just a few percent for typical comets, or that something fundamentally different was happening inside this ancient visitor. NASA's Neil Gehrels Swift Observatory provided the smoking gun evidence that confirmed what many had suspected, but few dared believe. On July 31, 2025, Swift's ultraviolet telescope made the first direct detection of hydroxyl radicals, O molecules that form when water vapor is broken apart by solar radiation. This detection provided unambiguous proof that 3I/ATLAS wasn't just reflecting sunlight off dust particles, but was actively sublimating pristine water ice that had been frozen solid for potentially 11 billion years. But the chemistry revealed by 3I/ATLAS proved to be far stranger than anyone had anticipated. As powerful ground-based telescopes and space observatories trained their instruments on this cosmic visitor, they uncovered a chemical composition that read like a periodic table from the galaxy's youth. Spectroscopic analysis revealed not just the expected water ice and rocky dust, but an exotic cocktail of molecules that painted a picture of planetary formation under conditions radically different from our own solar system's birth. The James Webb Space Telescope's infrared eyes peered deep into the comet's glowing coma and detected something remarkable: significant concentrations of carbon dioxide ice, far exceeding what's typically found in solar system comets. But even more intriguing was the detection of carbon monoxide, a highly volatile molecule that should have been among the first to escape during the object's billion-year journey through interstellar space. The presence of CO suggested that 3I/ATLAS had managed to retain some of its most fragile chemical components across cosmic epochs, preserved in the deep interior of its nucleus, like a chemical time capsule. Perhaps most shocking was the discovery of complex organic compounds scattered throughout the coma. These weren't simple molecules, but sophisticated carbon-based structures, similar to those found in the most primitive meteorites from our own solar system's formation. The fact that such delicate chemistry had survived the harsh radiation environment of interstellar space for billions of years suggested that 3I/ATLAS was far larger and more structurally intact than anyone had initially imagined. The Hubble Space Telescope's high-resolution imaging capabilities revealed another rule-breaking characteristic that left astronomers scratching their heads. Instead of the classic comet tail pointing directly away from the Sun, 3I/ATLAS exhibited what researchers described as a teardrop-shaped cocoon of dust and gas extending in multiple directions around the nucleus. Most bizarrely, a prominent plume of material appeared to be flowing toward the Sun, a seemingly impossible orientation that violated everything astronomers thought they knew about how comet tails form. This counterintuitive dust distribution initially raised eyebrows and fueled speculation about artificial origins, but detailed analysis revealed an even more fascinating natural explanation. The unusual tail structure indicated that 3I/ATLAS was experiencing anisotropic outgassing, material being ejected primarily from localized hotspots on the sun-facing side of a slowly rotating nucleus. The momentum of the ejected dust and gas was carrying it forward in the comet's direction of motion before solar radiation pressure could push it back into a traditional tail configuration. Ground-based observations coordinated through the global amateur astronomy community provided crucial details about the comet's rotation and structure. Using relatively modest telescopes but sophisticated analysis techniques, observers around the world detected periodic brightness variations that revealed 3I/ATLAS was spinning with a rotation period of approximately 16.16 hours. But unlike the dramatic brightness changes observed in Oumuamua, this ancient comet showed surprisingly stable light curves, with variations of only about 0.2 magnitudes throughout each rotation cycle. This minimal variability initially puzzled researchers who expected highly irregular objects to show significant brightness changes as different surface areas faced Earth during rotation. The relatively flat light curve suggested either a more spherical nucleus than anticipated, or a complex activity pattern that masked shape-related variations. The stable rotation also indicated that 3I/ATLAS was a structurally robust object, not a loose collection of rubble held together by weak gravitational forces, but a coherent body that had maintained its integrity across billions of years of interstellar travel. Spectroscopic analysis conducted by major facilities, including the Gemini North Telescope and the Very Large Telescope, revealed another chemical surprise. The reflected light from 3I/ATLAS's coma showed a distinctly reddish color, redder than our Sun, but similar to the most primitive D-type asteroids found in the outer regions of our solar system's asteroid belt. These D-type objects represent some of the most chemically pristine bodies known, characterized by dark, reddish surfaces rich in complex organic compounds that have remained largely unchanged since the solar system's formation. The spectral similarity between 3I/ATLAS and these primitive asteroids suggested that this interstellar visitor had formed from materials fundamentally similar to those that built our own solar system, but under chemical conditions that were subtly yet significantly different. Near-infrared observations revealed spectral signatures indicating the presence of approximately 10 micron-sized water ice grains within the coma, mixed with roughly 70% rocky material that matched primitive carbonaceous meteorites. some of the most chemically unprocessed materials known from our cosmic neighborhood. But perhaps the most remarkable discovery came from detailed chemical modeling of the coma composition. Analysis suggested that 3I/ATLAS represented an almost perfect aerial mixture of water ice and primordial rocky material, with proportions that closely matched theoretical predictions for planetesimal formation in metal-poor protoplanetary disks. This wasn't just an ancient comet. It was a direct sample of the raw materials from which planets formed when our galaxy was young and chemically simple. The detection of nickel vapor in the comet's coma provided the final piece of evidence that 3I/ATLAS truly was breaking all the rules. Nickel had never before been detected in the atmosphere of a comet from our own solar system. Yet here was this interstellar visitor, casually outgassing metallic vapors, as if such exotic chemistry was perfectly normal. The presence of gaseous metals suggested that 3I/ATLAS contained a higher proportion of refractory materials, substances that remain solid at high temperatures, than any comet previously studied. Every new observation of 3I/ATLAS revealed an object that seemed determined to violate astronomical expectations. It was simultaneously ancient yet active, chemically primitive yet remarkably complex, structurally robust yet actively disintegrating as it approached our sun. The comet had retained an extraordinary inventory of volatile materials across its billion-year journey through space, while also preserving delicate organic compounds that should have been destroyed by cosmic radiation long ago. As 3I/ATLAS continued its approach toward perihelion, astronomers realized they weren't just studying another interstellar visitor. They were analyzing a perfectly preserved sample of planetary formation from the galaxy's youth, a chemical fingerprint of cosmic processes that operated under conditions we can barely imagine. This ancient wanderer had become a Rosetta Stone for understanding how worlds formed when the universe was fundamentally different, carrying within its nucleus the direct evidence of chemistry and physics from an epoch that predated our entire cosmic neighborhood. The rules weren't just being broken. They were being completely rewritten by a visitor from the galactic dawn. Chapter 6. Theories, Speculation, and the Alien Hypothesis. When Harvard astronomer Avi Loeb first published his analysis of 3I/ATLAS's trajectory, the astronomical community held its breath. Here was one of the world's most respected theoretical physicists, the former chair of Harvard's astronomy department, suggesting that this interstellar visitor might not be what it appears to be. His calculations were precise, his methodology sound, and his conclusion unsettling. The probability that 3I/ATLAS arrived by pure chance was so astronomically low that perhaps we needed to consider alternatives that most scientists would never dare whisper in public. What if 3I/ATLAS wasn't a comet at all? What if it was something else entirely? Something designed? The alien probe hypothesis didn't emerge from fringe conspiracy forums or late-night radio shows. It crystallized from cold, hard mathematics and peer-reviewed statistical analysis. When multiple independent research teams calculated the odds of 3I/ATLAS's near-perfect ecliptic alignment, they arrived at the same disturbing number: 0.2%. Less than 2 chances in 1,000. When they factored in its unprecedented speed, its unusual chemical composition, and its eerily convenient trajectory that would allow systematic observation of all inner solar system planets, the joint probability dropped to levels that made even skeptical astronomers uncomfortable. But Loeb and his collaborators weren't content with statistical anomalies. They constructed what they called a convergence of impossibilities, a methodical catalog of characteristics that individually might be explained away, but collectively painted a picture that challenged every assumption about natural interstellar objects. The first impossibility was size. Initial brightness estimates suggested a nucleus nearly 20 kilometers across, making 3I/ATLAS potentially the largest solid object ever ejected from another stellar system. The physics of planetary formation and ejection mechanisms struggled to explain how something so massive could achieve the velocity needed to escape its birth system and traverse interstellar space. The second impossibility was trajectory precision. 3I/ATLAS wasn't just passing through our solar system, it was touring it. Its path would bring it within relatively close range of Venus, Mars, and Jupiter, a geometric alignment with a calculated probability of less than 0.005%. For a natural object arriving from the random depths of space, this seemed less like coincidence and more like intelligent route planning. The third impossibility was timing. The object's closest approach to the Sun would occur during solar conjunction, when Earth-based telescopes would be blinded by solar glare. This provided what Loeb termed a perfect concealment window, exactly when a hypothetical probe might execute a trajectory-altering maneuver to enter a bound orbit around our Sun, all while remaining invisible to human observation. The probability of this timing occurring by chance, roughly 7%. The fourth impossibility emerged from early spectroscopic observations. Unlike typical comets, which begin outgassing predictable volatile compounds as they approach the Sun, 3I/ATLAS initially showed a dusty coma, but no detectable emissions of cyanide, carbon compounds, or other standard cometary gases. For an object supposedly billions of years old and presumably loaded with frozen volatiles, this silence was deafening. Either it wasn't a comet, or it was unlike any comet in our experience. The fifth and perhaps most unsettling impossibility was velocity. At 58 kilometers per second relative to our Sun, 3I/ATLAS was moving too fast for humanity to intercept with current chemical rocket technology. If it were an artificial probe, this speed would represent a deliberate design choice, fast enough to avoid capture or detailed study by any civilization it encountered, yet slow enough to conduct meaningful observations during its passage. Loeb's team didn't stop at statistical analysis. They proposed testable scenarios that could distinguish between natural and artificial origins. If 3I/ATLAS were indeed a probe, they argued, it might attempt what aerospace engineers call a reverse solar Oberth maneuver during its hidden passage behind the Sun. By firing engines at the point of maximum velocity, a spacecraft could use the Sun's gravity well to amplify the effect of its propulsion, potentially breaking into a bound orbit with minimal fuel expenditure. The hypothesis gained credibility when other researchers began identifying additional anomalies. The object's rotation period of approximately 16 hours was unusually stable, lacking the chaotic tumbling expected from a natural body that had endured billions of years of cosmic bombardment. Its light curve showed minimal brightness variation, suggesting either a surprisingly spherical shape or a more complex geometry than typical asteroids or comet nuclei. More disturbing still were the implications if the artificial hypothesis proved correct. Some researchers, drawing on solutions to the Fermi paradox like the dark forest theory, suggested that 3I/ATLAS might represent reconnaissance by a civilization operating under the assumption that the universe was populated by potentially hostile intelligences. In this scenario, advanced civilizations would conduct careful surveillance of emerging technological species like humanity, gathering intelligence while maintaining strict operational security. The probe hypothesis gained additional traction when researchers realized that 3I/ATLAS's extreme velocity made it practically immune to human interference. Unlike slower interstellar visitors that might be vulnerable to interception by sufficiently advanced spacecraft, this object's speed placed it permanently beyond our technological reach. If it were indeed artificial, its designers had ensured that any intelligence gathering would remain uncompromised by the target civilization's response. But the astronomical mainstream wasn't prepared to accept extraordinary claims without extraordinary evidence. The scientific community's response was swift, systematic, and devastating to the artificial origin hypothesis. Leading researchers from institutions worldwide began methodically dismantling each supposed impossibility through careful reanalysis of the data and application of Occam's razor. The principle that the simplest explanation consistent with observations should be preferred. The size paradox dissolved when improved observations from the Hubble Space Telescope revealed that 3I/ATLAS's impressive brightness came not from a massive nucleus, but from an extraordinarily active coma. The actual nucleus was likely less than 6 kilometers in diameter, large for an interstellar visitor, but well within the range of natural formation and ejection mechanisms. The object's brightness had fooled early observers into overestimating its size by a factor of 3. The trajectory precision argument crumbled under geometric analysis. Close approaches to inner solar system planets weren't independent coincidences requiring separate explanations, but inevitable consequences of any path passing near the ecliptic plane. The controversial orbital inclination that enabled these encounters was the same characteristic that critics claimed demonstrated artificial design. The apparent fine-tuning was simply geometry, not intelligence. The concealment timing paradox evaporated when astronomers realized that solar conjunction wouldn't actually hide 3I/ATLAS from all observers. Multiple spacecraft throughout the inner solar system, including ESA's JUICE mission and various Mars-based assets, would maintain clear sightlines to the object during its solar passage. Any significant trajectory modification would be immediately detectable by these space-based observers, making the proposed stealth maneuver hypothesis readily testable and likely falsifiable. Most decisively, the spectroscopic silence was broken when NASA's Neil Gehrels Swift Observatory detected hydroxyl OH emission, the unmistakable signature of water vapor photodissociation. This confirmed that 3I/ATLAS was indeed outgassing like a normal comet, with the initial absence of other volatile species easily explained by the cold temperatures at its discovery distance. As the object continued approaching the Sun, additional expected cometary compounds began appearing in its spectrum, exactly as natural models predicted. The velocity argument, while factually correct, proved irrelevant to origin determination. Many natural processes could accelerate objects to extreme speeds, from gravitational slingshot encounters with giant planets to direct ejection during stellar close encounters or galactic tidal interactions. High velocity alone wasn't evidence of artificial construction. Perhaps most importantly, mainstream researchers pointed out that every unusual characteristic of 3I/ATLAS had natural precedents or explanations within established physics. While the combination of traits was admittedly rare events were expected to occur eventually given the vast number of stellar systems and ejected objects throughout the galaxy. The artificial hypothesis, by contrast, required invoking entities and technologies for which no independent evidence existed. The scientific establishment's rejection of the alien probe hypothesis wasn't based on dogmatic resistance to extraordinary ideas, but on methodical application of established evidentiary standards. Extraordinary claims required extraordinary evidence, and statistical improbability alone didn't constitute proof of artificial origin. The burden of evidence remained with those proposing technological explanations, not with researchers defending natural interpretations. Yet the controversy served valuable scientific purposes beyond its ultimate resolution. It forced astronomers to examine their assumptions about interstellar object populations, refine their statistical frameworks for evaluating unusual observations, and develop more sophisticated models of ejection mechanisms and galactic dynamics. The rigorous testing of extraordinary hypotheses strengthened confidence in conventional explanations, while establishing methodological precedents for future investigations. The debate also highlighted important philosophical tensions within scientific methodology. While mainstream astronomy applied conservative standards favoring natural explanations, some researchers argued for more aggressive investigation of low-probability scenarios that might indicate technological signatures. This tension reflected broader questions about how science should approach the search for extraterrestrial intelligence and the investigation of potentially paradigm-shifting discoveries. As 3I/ATLAS continued its journey toward perihelion, the alien hypothesis gradually faded from serious scientific consideration, overwhelmed by accumulating evidence of the object's natural, if remarkable, origins. But the controversy had already served its purpose, demonstrating that even the most extraordinary claims could be subjected to rigorous scientific scrutiny, tested against empirical evidence, and resolved through the self-correcting mechanisms of peer review and systematic investigation. The ancient comet from the galactic dawn had taught us as much about the practice of science as about the early cosmos it represented, showing that wonder and rigor could coexist productively in humanity's eternal quest to understand its place in the universe. Chapter 7. A Public and Scientific Sensation. The moment 3I/ATLAS burst into public consciousness, it triggered something unprecedented in the history of astronomy. A perfect storm of scientific discovery, viral fascination, and democratic participation that would forever change how humanity encounters visitors from the cosmos. This wasn't just another distant astronomical event relegated to academic journals and observatory press releases. This was a real-time cosmic thriller playing out across social media feeds, amateur telescope eyepieces, and conspiracy theory forums simultaneously, creating a new paradigm where cutting-edge science and public imagination collided at the speed of light. Within hours of the Minor Planet Center's announcement on July 2, 2025, number 3I/ATLAS began trending across multiple platforms. But this wasn't the typical fleeting internet sensation, driven by memes and speculation. Something fundamentally different was happening: the democratization of astronomical discovery in real time. For the first time in history, an interstellar visitor was being studied not just by elite observatories with million-dollar budgets, but by thousands of amateur astronomers armed with increasingly sophisticated equipment and an unprecedented level of global coordination. The astronomer's telegram became mission control for this distributed research effort, with updates flooding in every few hours from observers across 6 continents. Miguel Alcón in Spain reported tail measurements extending over 25,000 kilometers. Teams in Chile tracked brightness variations with precision rivaling professional facilities. Amateur astronomers in Japan provided crucial astrometric data during gaps in professional coverage. Each contribution was tagged, verified, and immediately incorporated into the evolving scientific understanding of this ancient wanderer. But what made this participation truly revolutionary wasn't just the quantity of observations. It was their quality. The accessibility revolution in astronomy, driven by digital cameras, computer-controlled mounts, and sophisticated analysis software, had created a generation of citizen scientists whose capabilities would have been unimaginable just decades earlier. High school students were capturing images that revealed structural details in 3I/ATLAS's coma. Retired engineers were conducting photometric analysis, sophisticated enough to determine rotation periods. Hobbyists with backyard setups were contributing data that professional astronomers eagerly incorporated into peer-reviewed publications. This wasn't merely crowdsourcing. It was collaborative discovery at a scale never before attempted. The traditional boundaries between professional and amateur astronomy didn't just blur, they evaporated entirely. When 3I/ATLAS displayed unexpected brightness surges, the first reports came not from Hubble or the Very Large Telescope, but from amateur observers who happened to be monitoring the comet during their regular imaging sessions. When subtle changes in tail structure became apparent, the global amateur community provided the temporal coverage necessary to track these variations across multiple nights and observing conditions. The viral nature of modern information spread transformed 3I/ATLAS into something far more complex than a scientific discovery. Social media algorithms, designed to maximize engagement, seized upon the most sensational aspects of the story. The alien probe hypothesis, the mysterious trajectory, the statistical impossibilities. Headlines morphed from measured scientific language into clickbait gold. Scientists baffled by mysterious space visitor. Could this be our first alien contact? The comet that's breaking physics. Each share, comment, and reaction fed the algorithm's hunger for engagement, amplifying controversial interpretations, while more nuanced scientific analysis struggled for attention. The careful hedging that characterizes good science, acknowledging uncertainties, presenting multiple hypotheses, explaining statistical limitations, proved no match for narratives offering simple, dramatic explanations for complex phenomena. The artificial origin hypothesis, initially proposed as one possibility among many by serious researchers, mutated through viral sharing into increasingly sensational claims that bore little resemblance to the original scientific arguments. YouTube creators seized the moment with content ranging from rigorous educational analysis to wild speculation. Channels dedicated to space exploration found themselves competing for viewers with conspiracy theorists who wove 3I/ATLAS into elaborate narratives involving government cover-ups, ancient alien visitations, and secret space programs. The comment sections became battlegrounds where serious astronomy enthusiasts debated orbital mechanics alongside users convinced that NASA was hiding crucial evidence about the object's true nature. TikTok videos reduced complex spectroscopic analysis to 60-second summaries, while Twitter threads attempted to explain hyperbolic orbits in 280-character installments. The challenge for science communicators became not just explaining what 3I/ATLAS was, but constantly countering what it wasn't, battling a hydra of misinformation that spawned new heads faster than facts could sever them. Yet within this chaotic information ecosystem, something remarkable was happening. Educational content creators discovered they could use 3I/ATLAS as a gateway drug to sophisticated astronomical concepts. The object's dramatic story provided the hook, but millions of viewers found themselves learning about orbital mechanics, spectroscopy, and the scientific method along the way. Physics concepts that typically remained locked in textbooks suddenly became relevant to understanding breaking news from space. The JPL Horizons website experienced unprecedented traffic as curious individuals learned they could track 3I/ATLAS's position in real time. Online calculators allowed anyone to determine when the comet would be visible from their location. Mobile apps enabled augmented reality viewing, overlaying 3I/ATLAS's position onto smartphone camera feeds. For the first time, a significant portion of the global population wasn't just reading about an astronomical discovery. They were actively participating in following its progress through space. This participation created powerful educational moments. Students who might never have engaged with astronomy found themselves calculating orbital periods, plotting light curves, and debating the merits of different spectroscopic interpretations. Teachers worldwide incorporated 3I/ATLAS tracking into their curricula, using the comet's journey to illustrate everything from Kepler's laws to the scientific method. The object became a living laboratory, demonstrating abstract concepts through real, measurable phenomena. The democratization extended beyond observation to analysis and interpretation. Open-source software packages allowed dedicated amateurs to process their own spectroscopic data, measure rotation periods from their photometry, and calculate orbital parameters from their astrometric positions. Online forums buzzed with technical discussions that would have been indistinguishable from professional conference presentations. The traditional gatekeepers of astronomical knowledge, journals, conferences, institutional affiliations, found their monopoly challenged by a global network of informed enthusiasts sharing data and insights in real time. But this accessibility came with its shadow side. The same tools that enabled valuable citizen science also facilitated the spread of increasingly elaborate conspiracy theories. Some online communities embraced scenarios involving multiple alien civilizations, using 3I/ATLAS as a reconnaissance probe. Others connected the object to ancient astronaut theories, suggesting it represented a return visit from extraterrestrial beings who had visited Earth in the distant past. Political conspiracy theorists proposed that governments worldwide were coordinating to suppress evidence of the object's artificial nature. The speed of information propagation in the digital age meant that wild speculation could circle the globe and become entrenched in online echo chambers before scientific analysis could address the underlying claims. Correction and clarification, the traditional tools of science communication, proved inadequate against viral misinformation that evolved faster than facts could chase it. Professional astronomers found themselves in uncharted territory, simultaneously grateful for the unprecedented level of public interest and global collaboration, while struggling to maintain scientific rigor in an environment that rewarded sensationalism over accuracy. Press releases required careful crafting to avoid providing ammunition for conspiracy theorists, while still acknowledging the genuine uncertainties inherent in cutting-edge research. The 3I/ATLAS phenomenon revealed both the incredible potential and serious challenges of science communication in the digital age. Never before had so many people been able to participate directly in astronomical research. Never before had scientific discovery unfolded so transparently and inclusively. But never before had the gap between scientific uncertainty and public demand for definitive answers been so starkly exposed. The object's story demonstrated that modern science communication requires new strategies, new tools, and new understanding of how information spreads in networked societies. The most successful educators learned to embrace the detective story aspects of the discovery. How astronomers use light curves to determine rotation periods. How spectroscopy reveals chemical composition. How orbital mechanics encode billion-year journeys across the galaxy. By presenting scientific analysis as cosmic archaeology, they made technical concepts accessible while preserving their essential content. Perhaps most importantly, the 3I/ATLAS sensation revealed that public fascination with cosmic mysteries remains as powerful as ever. Whether driven by hopes of alien contact, fear of the unknown, or simple curiosity about our place in the universe, millions of people engaged deeply with cutting-edge astronomical research in ways that would have been impossible just a generation ago. This engagement represents both an unprecedented opportunity and a profound responsibility for the scientific community. The chance to make genuine discovery accessible to unprecedented numbers of people. But only if researchers and educators can successfully navigate the complex landscape of modern media and communication. As 3I/ATLAS continues its journey toward perihelion, its impact on public engagement with science has already become part of its lasting legacy. The ancient comet has shown us that when cosmic discovery meets human curiosity in the digital age, the results are both inspiring and challenging, much like the mysterious wanderer that sparked the entire conversation. Chapter 8. Lessons for the Future. What 3I/ATLAS means for astronomy. As 3I/ATLAS continues its billion-year journey back into the cosmic void, it leaves behind something far more profound than just spectacular images and scientific data. This ancient messenger from the galactic dawn has fundamentally transformed how we approach the study of interstellar visitors, marking the end of one era in astronomy and the explosive beginning of another. We stand at the threshold of a revolution that will make the discovery of 3I/ATLAS look like merely the opening act of humanity's greatest cosmic detective story. The transformation begins with a simple but staggering realization. We are no longer alone in our ability to detect these cosmic wanderers. For decades, interstellar object discovery proceeded at a frustratingly slow pace. 3 confirmed visitors in 8 years, each one a precious anomaly that sparked more questions than answers. But 3I/ATLAS represents the final discovery of the current generation of sky surveys, and what comes next will change everything we thought we knew about the galaxy's hidden population of planetary refugees. The Vera C. Rubin Observatory, whose pre-discovery imaging of 3I/ATLAS provided a tantalizing preview of its capabilities, is about to unleash an unprecedented revolution in cosmic archaeology. This technological marvel combines an 8.4-meter primary mirror with a 3.2 gigapixel camera, creating a systematic surveying machine that will image the entire visible sky every few nights with sensitivity that dwarfs current capabilities. Where today's surveys might detect one interstellar visitor per year, Rubin projections suggest we could be discovering dozens, perhaps even hundreds, during its first decade of operations. Think about what this means for a moment. Instead of treating each interstellar object as a unique curiosity to be studied in isolation, we're about to build statistical samples large enough to answer fundamental questions about planetary formation throughout the galaxy's entire history. We'll trace chemical evolution across cosmic time through direct analysis of objects that formed under conditions no longer present in our local galactic environment. We'll discover which stellar systems are most prolific at ejecting planetesimals, how different metallicities affect planetary building blocks, and whether the processes that created our solar system represent typical or exceptional circumstances in galactic history. But the revolution extends far beyond mere discovery rates. The extended detection range and early warning capabilities of next-generation surveys will transform how we study these cosmic visitors, from reactive science to proactive archaeology. While 3I/ATLAS was detected relatively early in its approach, providing months of observation time, future surveys will routinely spot objects years before their closest approach to the Sun. This extended timeline opens unprecedented opportunities for detailed characterization, international coordination, and even spacecraft intercepts that would have been impossible with current discovery timelines. ESA's Comet Interceptor mission, scheduled for launch in 2029, exemplifies this forward-thinking approach. Rather than targeting a predetermined object, this spacecraft will wait in a parking orbit at the Sun-Earth L2 point, ready to be rapidly deployed when surveys discover a suitable target, either a pristine long-period comet from our own Oort cloud, or, in the most scientifically exciting scenario, a newly discovered interstellar visitor on an interceptable trajectory. The spacecraft carries instruments designed for comprehensive characterization of previously unstudied objects, promising our first close-up examination of materials that formed around distant stars billions of years ago. The scientific justification for such ambitious missions becomes stronger with each new interstellar discovery. 3I/ATLAS has demonstrated that these objects carry irreplaceable information about planetary formation processes under conditions vastly different from those that created our own solar system. Its ancient thick disk origin, with an estimated age of 7 to 11 billion years, provides direct evidence that substantial water-rich planetesimals were forming efficiently in the metal-poor environment of the early galaxy, a discovery that pushes back the potential timeline for habitable world formation by billions of years. This revelation has profound implications for astrobiology and our understanding of when and where life might have first emerged in the Milky Way. If large water-bearing planetesimals were common in the ancient galaxy, then the chemical prerequisites for life, water, organic compounds, and complex chemistry, were being distributed throughout stellar systems far earlier than previously thought. 3I/ATLAS itself carries spectroscopic evidence of primitive organic-rich material, similar to the most chemically primitive meteorites in our own solar system, suggesting remarkable consistency in the basic processes of planetesimal formation across vast differences in stellar metallicity and galactic epoch. The technological ecosystem that enabled 3I/ATLAS's discovery and characterization provides a blueprint for studying future visitors. The seamless integration of space-based and ground-based observations, from initial detection by the ATLAS survey to detailed spectroscopy by the James Webb Space Telescope, demonstrates how modern astronomy has evolved into a truly global, collaborative enterprise. Amateur astronomers contributed genuinely valuable data through sophisticated equipment and analysis techniques that rival professional facilities from just decades ago, while rapid communication networks enabled real-time coordination of observations across multiple continents. This democratization of cosmic discovery represents more than just a technological advancement. It's a fundamental shift in how scientific research operates in the digital age. The astronomer's telegram became mission control for a distributed observation campaign that engaged professional observatories, university research groups, and citizen scientists in a coordinated effort that would have been impossible during previous interstellar visits. When the next wave of discoveries begins, this collaborative infrastructure will be ready to extract maximum scientific value from each detection. Perhaps most importantly, 3I/ATLAS has established methodological precedents for evaluating extraordinary claims about potential technological signatures in astronomical data. The rigorous investigation of its unusual orbital characteristics, statistical anomalies, and spectroscopic properties demonstrated how science can address even the most speculative hypotheses through testable predictions and objective measurements. While the artificial origin hypothesis ultimately proved unsupported by evidence, its systematic evaluation strengthened confidence in conventional explanations while establishing analytical frameworks for future investigations of potentially anomalous objects. The controversy surrounding 3I/ATLAS also revealed both the opportunities and challenges of science communication in the digital age. Social media platforms enabled unprecedented public engagement with cutting-edge astronomical research, allowing millions of people to follow along with active scientific discovery in real time. However, the same networks that facilitated valuable citizen science also enabled the rapid spread of misinformation and speculation, demonstrating the need for scientists to develop new strategies for communicating complex, uncertain, and evolving research to public audiences. Looking ahead, the lessons learned from 3I/ATLAS will directly inform how we approach the dozens or hundreds of interstellar visitors that await discovery. The observational protocols developed for its study, the international collaboration frameworks established during its characterization, and the data analysis techniques refined through its investigation provide a foundation for systematic interstellar object science. Future discoveries will benefit from standardized response procedures, pre-negotiated telescope time allocations, and coordinated spectroscopic campaigns that maximize scientific return from each detection. The most profound legacy of 3I/ATLAS may be philosophical rather than purely scientific. This ancient wanderer connected us viscerally to the deep history of our galaxy and our place within a community of worlds that extends across space and time. It demonstrated that planetary formation is not a local phenomenon confined to our solar system or stellar neighborhood, but a galactic process that has been operating throughout most of cosmic history. We are not alone in our corner of the galaxy, not because 3I/ATLAS carried signals of intelligent life, but because it proved that the building blocks of planetary systems and potentially life itself have been forming and dispersing throughout the Milky Way for most of its existence. As this billion-year-old messenger disappears into the constellation Draco and resumes its eternal journey through interstellar space, it carries with it humanity's first deliberate signals to the cosmos beyond our solar system. Radio transmissions from Earth, traveling at the speed of light, will eventually overtake the ancient comet and continue outward into the galaxy, marking this moment when a 4.6 billion-year-old civilization briefly encountered an 11 billion-year-old wanderer from the galactic dawn. The story of 3I/ATLAS ultimately demonstrates that the most profound scientific discoveries often emerge not from finding what we expect, but from carefully studying what surprises us. This rule-breaking visitor has taught us as much about the practice of science as about the ancient cosmos it represents, showing that wonder and rigor, speculation and skepticism can coexist productively in the endless human quest to understand our place in the universe. The eternal journey continues, and we are now better equipped than ever to understand the messages it carries. Every future interstellar visitor will be studied using methods pioneered during this ancient comet's brief residency in our cosmic neighborhood, each one adding new pieces to the grand puzzle of planetary formation throughout galactic history. 3I/ATLAS came to us from the dawn of time, and in studying it, we have glimpsed both our cosmic past and our astronomical future. That's a wrap on this incredible journey through the cosmos with 3I/ATLAS, the most rule-breaking interstellar visitor we've ever encountered. From its impossible speed to its ancient origins, from the heated scientific debates to the global collaboration that studied it, this cosmic wanderer has fundamentally changed how we understand our place in the galaxy. If you found this deep dive into cosmic mysteries as fascinating as I did, please hit that subscribe button and ring the notification bell. The Sleep Lab has so much more to explore together. Whether it's the next interstellar visitor, mysterious exoplanets, or the mind-bending physics of black holes, we'll be here to unravel the universe's greatest secrets, one discovery at a time. Thanks for joining me on this astronomical adventure, and sweet dreams under the stars.